Great. I'm really happy your dog likes my lectures. On Friday we talked about equilibrium in 3 dimensions, right? So we talked about different connection types, and we went through and looked at the different connections and how they resist motion, and that allowed us to determine the directions in which they'll have a reaction, right? So here we have a bearing, and we think about this bearing here would resist motion in the y direction and in the z direction, and therefore we put an unknown reaction force, cy and cz, at that point. Same thing over here at B. This bearing is going to resist motion in the z direction and in the x direction. All right? Neither of these are really built to resist a moment in any direction, right? That's not how these bearings are built. So we just say these are the 2 directions. Okay? Lots of people have been asking, do I need to go memorize all those 3-dimensional ones? Well, you can, or you can work enough problems to get used to kind of thinking about them as in what motions is this joint designed to resist. And I think that's a better process, because when you become an engineer, you're going to be designing something, and it's not going to be a bearing here maybe, but it's going to be, maybe it's a bolted flange, but it's a flange, right, that only has a couple bolts in it. And so we want to think, are we sizing those bolts so that they resist a twist? Or are we sizing them so that they, in kind of along this axis here, are we sizing them for that twist? Are we sizing them for twist about this axis? How are we deciding, right? And as you do your design, you might want to say, you know what? We're going to put these bolts into sheetrock, okay? It's not going to have any force to pull out force, right? Like when you hang a picture on the wall. Anybody ever hung a picture on a wall in sheetrock? Okay? And you can put that anchor into the wall, and it will hold really well if you pull straight down on it right at the wall. But if you grab that thing with a set of pliers and pull on it, what's going to happen? You're just going to break that sheetrock right out of the wall, right? You're going to make a big giant mess. So if I were thinking about this and I were trying to analyze this this joint, or this the reaction forces at this point, would I say that the sheetrock, that the anchor has any force in and out of the wall? No. It does. I mean, it's got a couple pounds, but not a lot, right? I'd say, oh yeah, maybe it can hold 50 pounds in the y direction. So I'd be like, yeah, that's fine. But I would not say that it could hold anything coming straight out of the wall, right? So that's what we're doing here. You could look at how the book simplifies simplifies joints and says, well, if you have a bearing, it's got the x and the y. But we're actually, though, where we're going is we're going to say, oh, look at that joint right there. It's not a bearing, but we're going to treat it as only resisting in the x and the y, right? It may be welded, but we're going to say it only resists motion in the x and the y because it's not designed to resist it in the z, all right? Then we did some problems where we figured out some unknowns. So there's 2 ways to do these problems. There's a scalar way and there's a vector way. So let's do this one using the scalar method. Okay? So to determine the force developed in the short link BD, we've got to find BD. There it is. Here's BD. And the tension in the chords CE and CF. CE and CF. And the reactions of the ball and socket joint at A on the block. Here's that. Okay? So anybody remember what types of motion a ball and socket resists?
No, it's all the forces.
All the forces, right? None of the moments. So it allows you to do this, right? You can move the pin everywhere, but you can't move the tip of the pin. Okay? So if we were drawing our free body diagram, which let's actually do that because I think you all can draw this box again. I believe in your art skills. Get a ruler out or something. So here's the free body diagram. We've removed it from its surroundings, And now we're going to put our unknowns on it. Or we'll put all the forces on it, I guess. We're going to have a force that I'm going to call FBD. We're going to have a force going this way that is FCF. A force going up that I'm going to call FCE. We'll have 9 kilonewtons going down. And we'll have 6 kilonewtons going this way. And then over here at A, we're going to have A sub Z. We're going to have A sub X. And we're going to have A sub Y. Okay? So how many unknowns do I have? 6. How many equations can I write in 3 dimensions? 6. Okay? So this should be solvable. All right, so let's try and write those equations. Sum of the forces in the x direction has to equal 0, and x is kind of down and to the left. So what things act in the x direction? AX plus 6 kilonewtons. Anything else? FCF. Does FCF act in the positive or the negative direction? Negative. So this is really important that we follow our sign convention and we put the appropriate SIGN sign in there. Okay? For this to be an equilibrium, what does the sum of those forces have to equal? 0. Okay? Give you a minute to do some of the forces in the y. What'd you find? Just AY, right? So then AY equals 0. Look at that. We are 20% there. Ding! Okay. Some of the forces into Z. We got a whole lot of them, right? Looks like we have FBD plus FCE plus AZ minus 9er, right? Equals 0. So I have 1, 2, 3, 4, 5 unknowns. And I have 2 equations. Can't solve it yet, right? Okay. Moments. Let's do the moments. Sum of the moments, about the x-axis has to be equal to 0. So that's going to be, I like to draw a little arrow and then the curly for what direction's positive. Okay. So do FBD, AZ, AY, or AX cause any moment about the x-axis? None of the A's, because A is on the x-axis, right? FBD goes through the x-axis, right? How about 6 kilonewtons? Does it cause a moment about the x-axis? Why not? It's parallel, okay? Same with FCF. So it looks like what we have causing moments about the x-axis would be 9 kilonewtons times its distance off the x-axis, which is 3 meters. Now, is that positive or negative? Well, no, just the whole sense of the moment. It's negative, right? Because if I curl in the direction of the vector, I'm going in the negative x direction. So that's going to be negative 9 times 3 plus FCE times 3 equals 0. Now, is FCE positive or negative in the moment sense? Positive. So we just found out FCE, right? What's FCE have to be? FCE is going to have to equal 9 kilonewtons, right? So we can go back here and say, oh, this is 9, right? Then we'll sum our moments about the y-axis. That's going to be this away, and positive would be like that. So here's the y-axis in our drawing, right? It's coming out right here. So it looks to me like I can eliminate 6 kilonewtons, AY, AX, FBD, and FCE. Because they go through the axis. The line of action passes through the axis. 6 kilonewtons passes through the axis. A sub x passes through the axis. A sub y is parallel, so it doesn't cause a moment about it. Okay? So then that leaves me A sub z times 4 meters, positive or negative? Negative. What else? Yeah. Positive or negative? Positive 9 kilonewtons times 4. Anything else? Yep. Positive or negative? Negative. Good job. And I think that's it. So that's going to be equal to 0. Okay, so can't solve that one quite yet. Let's do one more. Solve the moment about the z-axis, which we're straight up. So positive is going to be this away, equal to 0. Who can identify one? FCF. Yeah, FCF, positive or negative? Positive. And the lever arm for that guy is going to be 3. Somebody else have one? 6 kilonewtons. Yes, positive or negative? Negative 6 kilonewtons. And that lever arm for that's also 3. Anyone have one more? AY? Positive or negative? Positive AY times 4. I think that's it, right? Yep. Equals 0. All right.
Attention, attention. May I have your attention?
All right, we're going to pause for the drill now.
Attention.
All right, so that concludes our active shooter drill. So we're left with these equations. Let's see, I think we have one. Do we need this? Do we know FBD yet? No. Nope, so we'll need to solve that one. We know that one. 3, 4 equations. And it looks like we've got 1, 2, 3, 4 unknowns. Oh, AY we know is 0 though, so we could take it out of this one. Right? And if we know FCE is 9, yeah, so we could get FCF right off the bat. It looks like it's 6, right? If AY is 0, then FCF is clearly 6. And if knowing FCF is 6, then we know AX is 0, right? Yep. knowing FCF is 6, we could come up here and it looks like AZ, let's see, oh no, we'd actually have to do the math on that one. Darn it. 6 times 1.5 would be 9, right? Yep. So then it would just be 3 times 9, which is 27, divided by 27 divided by 4. Oy, 6.66, I think. Is that right? 27 divided by 4? What's that?
6.75.
All right. Okay, questions about how to solve these? It's just a... we didn't get FBD, but we could get it now by substituting in 6.75 and 6. So we have 12.75 minus 9 would be 3.75. So FBD would be negative 3.75. That can't be right. 9. Yeah. And AZ. Oh yeah, sorry. So it's 6.75. FCE is 9. AZ, what did we find? AZ is 6.75, and is it positive? No, I think it would be negative. Negative 6.75. So we'll have FCE of 9 minus 6.75 minus 9. So it looks like FBD is 6.75. Okay. All right. So then the last style of 3D equilibrium is where we have to use vectors, Victor. Okay. This is even more. I wouldn't say it's even more. This is just, it's going to, again, be keeping track of our 6 equations, right? So if we draw our free body diagram here, we knew there was a ball and socket, and that's at D. So we're going to have dx, dy, dz. Out here, we're going to have some force down, and I think, does it tell us what it weighs? 200 kilograms. So we're going to have 200 G going down, 200 times the acceleration of gravity. So 200 times 9.81 is 1860? 1960? 1960 newtons, we'll call it. Okay. And then we'll have TBA and TBC. All right. So let's start. We're going to have to turn TBA and TBC. We're going to have to find those guys. The way we'll find them is by unit vector. So RBA, see, I go in the x direction, it looks like I go positive 2I. In the y direction, it looks like I go minus 3J. And in the z direction, that's, yeah, minus 6. Okay? So that means that UBA, we're probably starting to recognize that if something has a 2, a 3, and a 6, then its magnitude is 7, right? So we could say it's 2/7 I hat minus 3/7 J hat minus 6/7 K hat for unit vectors. Then we'll do similar for RBC, which would be in the I hat direction, looks like negative 6 I hat. And in the J hat direction, negative 3 J hat. and negative 6 k hat. So that's 36 and 36 is 72, plus 9 is 81, so it's 9. So UBA, just finding the unit vector here, would be negative 6/9 I minus 3/9 j minus 6/9 k. Excuse me? Sorry. Yep, UBC. Okay. So what this tells me is that I need to put TBA in vector format. I just multiply it by its unit vector. So the vector TBA is going to be the magnitude TBA times 2/7 in the I hat direction minus TBA 3/7 j hat minus TBA times 6/7 k hat. And same thing for TBC. It's just going to be TBC times negative 6/9 is 2/3 I hat minus TBC, oops, and this should have been negative up here. Oh, I guess I would put the negative in there, that's fine. Minus TBC times 1/3 j hat minus TBC times 2/3 k hat. Everyone all right with this? And then we could see that D sub z is all in the k hat direction. D sub y is in the j hat direction. D sub x is in the I hat direction. And we have minus 1960 newtons in k hat. So it's these 1, 2, 3, 4, 5 unknowns that we're trying to solve for. So the way we do that is we go to our equations of equilibrium, sum of the forces in the x direction. So let's start over here with sum of the forces in the x has to equal 0. Again, I'll say x is down and to the left. So what has a component in the x direction? Looks like dx does. So I'll say d sub x. And none of these do. So then I'll just have plus 2/7 TBA minus 2/3 TBA equals 0.
TBC.
Ah, yes, thank you. TBC. All right. How about you do some of the forces in the y direction then? Anybody come up with a value? Or an equation, I guess? dy, that's a good place to start in the y direction. dy. Anything else? Minus 3/7 TBA. Minus 1/3 TBC. Equals 0. Sum of the forces in the z direction has to equal 0. Up is positive. In the z direction, I'll have dz minus 6/7 TBA minus 2/3 TBC equals 0?
No,
Minus 1960. Good job. Equals 0. Or you could say equals 1960, but don't jump ahead too much. When I do, I get in trouble. Okay? So now we can go through and say, I'm going to label these x, y, and z because they're already x, y, and z. And then I'm going to have to come up with some terms for this, like on my calculator I think I have a t, so I'll call these t. And then, what else do I have on my calculator?
You have A, B, C, and D on mine.
Yeah, maybe I'll call it b. Right? So it looks like I have 1, 2, 3, 4, 5 unknowns and only 3 equations. So I got to write me some more. Okay? Where would you get... yeah, well... yeah. Yeah. No, I didn't lead you astray. I was just doing some thinking. It's always good when you're teaching to think just a little bit. Okay? So let's sum the moments about the x-axis and say they have to be equal to 0. Okay? Well, I'm just going to sum it about the axes. I'm going to do all 3 axes. Yeah. So x-axis is down and to the left. So that means positive is that way. Okay. So things that cause moments about the x-axis, not dy, not dz. Does the 1960?
Yeah.
You betcha.
Negative.
You betcha. So it's going to be 1960, and I hear a negative being thrown out, right? Because if I go this way, it's going negative. So it'd be negative 1960 times what's the lever arm? No. No. 4 meters. Right? 4 meters, because it's the distance from the x-axis. Okay? What else causes a moment about the x-axis? TBA? Yep. TBA definitely does. So let's figure out the distance is going to be 6 meters. And it looks like it's positive. So let's say plus 6 meters times the y component of that. What's the y component of TBA? No, I'm working on TBA right now. So TPA looks like it's 3/7 in the j direction, right? So I'm going to say 3/7 TBA.
So when that 6 becoming negative, so if you're working on TBA, TBA is the one that's coming towards us.
Yep, but I'm taking the moment about the x-axis, so I'm going off that way, right?
Yeah.
Okay. Does everyone understand where this is confusing right now?
Why is it 6?
Yeah, I don't get the 6 meters.
Because I'm saying TBA acts right here at B, and it's 6 meters off of the x-axis.
Okay.
Right? So I'm looking at the y component of it that goes in that direction. Right? So this would be 3/7 TBA, right? If I break TBA into components, which I've done, it's going to have some in that direction, some in this direction, and some straight out. So the only one that causes a moment about the x-axis, right, is the y component, right? Thumbs up, thumbs down. You understand that why it's the y. Why it's the y. Okay? So let me isolate just that one. I'm going to try a new drawing over here, okay? So where's my red pen? Here it is. TBA is a vector that does this, right? And it's 6 meters from the point we're interested in. But we can break it into components, which we've done using the unit vector, which says 3/7 of TBA acts in the y direction. 6/7 of TBA acts in the z direction. And then what did we have for 2/7 of TBA acts along the x-axis, right? Everybody good with how I broke this into the three components of the unit vector, right? So then if we look just at the 2/7 TBA, it's parallel to the x-axis, so no moment, right? If I look just at the z, it goes through the x-axis, so no moment. So I'm only left with 3/7 TBA in the y direction that is 6 meters off of that x-axis. Better? Okay. Let's see. So then we're also going to have the moment about the x. We're going to have some TBC in there. So it looks like TBC has a 1/3 j, and it also is 6 meters. So 6 meters times 1/3 TBC. Anything else? Got that one. Yeah, I think that's it. So that equals 0. Now we can sum the moments about the y-axis, and that's going to be that way, with that way being positive. So none of these guys cause a moment about the y-axis. Does the 1960? A little bit, right? Positive or negative? Positive. 1 meter is its lever arm. Good job, Michael. Okay. And then what component of TBA is going to cause a moment about the y-axis? The x, right? So the x component of TBA, 2/7, looks like it'll be positive. So plus 6 meters times 2/7 TBA. And then I'm going to say it's going to be minus 6 meters times 2/3 TBC equals 0. Right?
And that's all we need.
That's 5 equations, and that should be all we need to solve now.
We could write a last one, but it's redundant, so it's just not needed.
Yeah, well, there actually would be none. So think about if we did the last one. Let's sum the moments about the z-axis. Say they're equal to 0. Here's z. What causes a moment about the z-axis? Nothing, because nothing doesn't pass through the z-axis, or this one's parallel to the z-axis, so there's just no equation to write there. Okay? So then we could go back through and say, okay, I think I called TBA as T, right? And TBC we said is B. So now I have 5 equations with 5 unknowns, and you can solve those. And this is where I just feel older every year, because I get to say when I was a boy, I had to solve those by hand. I don't recommend you do that now. I'd like you all to put this in your calculator now and make sure you can do it, because you didn't do the cross product in your calculator on the exam. And so I want to make sure you get your calculator so it's your good buddy.
How long did it take you to do this by hand?
Not that long. How long would it take me now to do by hand?
Yes.
Much longer.
So you do all five.
Yes, sir.
Question. On two force load factors, so the
It's gonna be more than that. Yes, it can be more.
two,
It's just more though because my hand has had, if
what's it
my
called?
calculator has issues sometimes with solving equations that sometimes. Yeah,
Two force.
So one of the things you have to keep in mind too.
It's from the
when you're
electrode, right?
doing systems
Two force
and stuff,
members?
you have to do a
Yes.
linear system instead of a
How
regular
do you
system.
know
So
what
all you
direction
should have to
equal
do
and
is add the
opposite
letters
is?
by hand in front.
It doesn't matter.
You
It'll
can actually type these in.
fall out in the solving usually.
It will?
Yeah, cause it's like
Mhm.
my
Because like,
calculator, like
in
sometimes
the
seriously
example
it
where
spits
you
out
had
an answer
the
right away and other times it will not.
strut from the plane,
Look into the using,
You used
there's
the-
actually points where I think it's,
the force on
can't
the
remember what class, there's
AC
a point where
member as going out, and I
half the
didn't know
time
how
you
you
won't
knew
do the
which
answer
one
unless
was,
you use the
which
linear
direction
solver.
it was.
And it puts it in
Yeah,
like
you
a
can
linear,
just
like, matrix,
assume
you
it,
have your, like,
and then it will fall out. If
basically
you
I, J, K,
follow
and
the
then
way
you
you
have
draw it in doing your math,
Yeah,
it'll
I'll
come out that
definitely
way. Yep.
consider that
Alright.
because
Do I have
that's
to
weird
see
though,
solve
because
this
like
because
otherwise like I'll try and like
center?
restructure the equation so
Or do
then
I have
I
to
get
define
there
this?
isn't that
You shouldn't even need to
intentional.
see solve, you should literally just have to, because I plugged mine in and she did the same thing with hers and it seemed
Are
to
you
work.
just plugging everything in? Yeah, gotcha, that's why.
Yeah, I mean, I did mine as a regular solve.
So here are the values I got. Is this what you all got?
Y'all ready for this?
Yeah.
Okay.
One sec, I'm just checking. That's close enough. Okay, so.
So just using the solve command, you have to use alpha for, I called it B, but it'll just solve it out for you. Okay? All right, so we will stop there for today. I would like you to do problems. These are the very end of chapter 5. So this was 5. 5, 6, 5, 7. So do some problems from 562 all the way up to 585. Pick some problems in there and do them, okay? Pick whichever ones you want. The one we just did is 570. But pick some problems in there. Do 3 or 4 until you feel pretty good about it. Now, if you are doing the problem and you're like, you know, this isn't that much fun, I agree, right? Like, because I guess I want to temper my comments earlier of you need to be motivated to do this because you like it. Dude, some of these, this isn't like, I don't just get super excited about doing this, but I can see how this is what I want to do. And knowing how to find these forces, that's important. Being able to solve puzzles like this, that's important. So don't be too hard on yourself if you're like, actually, no, this feels like work. Yep, it is work, right? But hopefully it's work that's more stimulating to you than digging a ditch. Okay? So.